everyone. My name is Sona Martin. I'm from the Department of CSE branch, 3rd SEM B section, Pesitam College, Shivamoga. So today my topic is about the signed operand multiplication and booth algorithm from the module 4 of computer organization. So first of all, before moving to my topic, I would like to give a brief introduction about my topic. So the multiplication of two fixed point binary number in signed magnitude representation is done with process of successive shift and add operation. Finally, numbers are added and the sum form the product. The sign of the product is determined from the sign of the multiplicand and the multiplier. Both algorithm gives a procedure for the multiplying binary integers in signed 2's complement representation in effective way, that is less number of additions or subtractions required. The multiplicand is subtracted from the partial product upon encountering the first least significant one in a string once in the multiplier. Next, I would like to tell you what are the main concepts that are my objectives of my concept of this presentation. So first of all, I will be explaining what is a signed operand multiplication and what is a booth algorithm, and then we need to know what are the procedure as well as the conditions when we do the booth algorithm multiplication, and then the examples to for the better and the more clarifications I will be explaining the examples for the booth multiplication using positive integer as well as a negative multiplier. First of all, the signed operand multiplication. As we know that multiplication of 2's complement, signed operands generate a double length product. So here we need to consider the two cases. In the first case, we will be considering using a positive multiplier, and in a second case we will be considering a negative multiplier. So first of all, let us consider the positive multiplier and negative multiplicand. So when we add a negative multiplicand to a partial product, we must extend the sign bit value of the multiplicand to the left as far as the product will extend. To understand it in better, for example, we can take a 5-bit signed operand, that is minus 13. As we know that minus 13 is a 5-bit operand with a negative multiplicand. So minus 13 is the negative multiplicand and it is multiplied by plus 11, which is a positive multiplier. And we know that we will get a 10-bit product, that is minus 143. Thus the hardware can be used for negative multiplicands if it is provided for sign extension of the partial product. And in the second case, we need to consider a negative multiplier. A straightforward solution is to form the 2's complement of the both multiplier and the multiplicand and proceed as in the case of a positive multiplier. This is the possible because complementation of both operands does not change the value or the sign of the product. A technique that works equally well for the both negative and the positive multiplier is called as the booth algorithm, which is I'm going to be explaining for the further. So now I'll be explaining about the booth algorithm multiplication. So first of all, we need to know what is a booth multiplication algorithm. So booth multiplication algorithm, it is a multiplication algorithm that multiplies two signed binary numbers in 2's complement notation. In booth algorithm, the left shift of the multiplicand has the effect of shifting the intermediate product to the left, just as when we are multiplying. The right shift of the multiplier prepares the next bit of the multiplier to examine in the iteration. Booth algorithm, it is a kind of algorithm which is more over a straightforward approach towards the algorithmic multiplication. This algorithm also has the benefit of the speed up the multiplication process, and it is also a very effective multiplication too. The representation of the multiplicand and product are not specified typically. These are both also in 2's complement representation like the multiplier, but any number system that support addition as well as subtraction will work as well. Booth's algorithm examines adjacent pairs of bits of the n bits multiplier y in signed 2 complement representation, including the implicit. Next, the further will to understand more about this both algorithmic multiplication, it is better if we take an example of a positive as well as a negative multiplier as our example, and will be understanding the concept a bit more. So before moving to the examples of this binary, both multiplication algorithm, first of all we need to know the procedures as well as the conditions which is to be known before we do a both multiplication. So first of all, in a procedure, the first procedure, there are four main procedure which we need to follow. At first, that is nothing but let m be the multiplicand, and the second let q be the multiplier, and in third, considering a 1-bit register, that is q minus 1, and we need to initialize it to the 0. And in fourth case, considering a register a, and we need to initialize this register a as well as to 0. These are the four procedures which we need to know while we do the both algorithmic multiplication. And as well as there are few conditions, actually majorly there are 3 conditions which we need to know while we do the both algorithmic multiplication. The first condition is if q0 into q minus 1 are same, that is they might be both 0 and 0 or 1 or 1. That is q0 is 0 as well as q minus 1 is 0, or else q0 is 1 as well as q minus 1 is also 1. If they are both same, then perform arithmetic right shift by one condition. And in second, if q0 into q minus 1 is equal to 1 0, that is q0 is 1 and q minus 1 is 0, then we need to perform that a minus m is leads to a, that where, and also then perform the arithmetic right shift. This is the second condition. And in third condition, if q0 into q minus 1 is 0 into 1, that is q0 is 0 and q minus 1 is 1, then a plus m leads to a, and then we need to perform the arithmetic right shift. These are the 3 main conditions which we need to keep in our mind when we do the both algorithmic multiplication. So now I have said you the explanation, procedure as well as the conditions of a both multiplication algorithm. So now let's see, for the better clarification and understanding of the both multiplication, let us take an example of a positive numbers, that is plus 23 and plus 19. This is just an example which we are taking to explain the both multiplication of the positive numbers. As we know, in the decimal form, 23 into 19, which is a product, that is 437. So we need to know how can we multiply 23 into 19 in binary form using both algorithmic multiplication. So as we all know, here 23 is our multiplicand which is multiplied by 19. So 19 is also the multiplier, and the 437 is the product. So we know that how can we represent 23 in binary form, that is 10111. This is the binary form of the 23 plus 23, and which is a multiplicand. And plus 19, which is in a decimal form, we know the binary form of plus 19 is 10011, and which is the multiplier. So in order to multiply 19 into 23, first step we need to see the rightmost bit of the multiplier, that is the rightmost first bit, which is 1. This 1 is multiplied by the 5 bit of this multiplicand. So as the result we will get the product 1 into 1 is 1, 1 into 1 is 1, 1 into 1 is 1, 1 into 0, 0, and 1 into 1, 1. This is our first product. That is the first right shift of the multiplier is multiplied with the 5-bit multiplicand. So the product will be 10111. And now keeping the rightmost first bit aside, taking out the rightmost second bit of the multiplier, which is again 1. So again this 1 multiplied by the 5-bit multiplicand, that is 10111, will be obtained with the product, that is 10111. This is our second product. And now next step, we are considering the third rightmost bit of the multiplier, which is 0. As we all know, 0 multiplied with any of the other numbers, the product is also 0. So 0 multiplied by 1, 0, 1, 1, 1, the product obtained is also 0, 0, 0, 0, 0. And then taking off the fourth right bit of the multiplier, which is again 0. So 0 again multiplied to the multiplicand, that is 1, 0, 1, 1, 1. The result obtained will be 0, 0, 0, 0 and 0. And then we are moving on to the last bit of the multiplier, which is 1. So now the 1 again multiplied by the multiplicand, that is 1, 0, 1, 1, 1. The product obtained will be 1, 0, 1, 1, 1. So the main thing we need to keep in our mind is the first, after multiplying, means after multiplying the multiplier, multiplying the right bit of the multiplier to the multiplicand will be obtained with the product. So leaving on to the first term, we need to leave the space on the right side of this term, and then we need to continue the products. So at the end we need to get the, as we all know, we need to get the answer of plus 437, that is 437. Here we can see we'll be adding all this product term, that is 1 is all, however the product is 1, 1, 1, 0 with carry 1. So 1, 1, again 1 with 1 carry 1. So 1, again 1, 0 with carry 1, again 1, 1 carry 1, 1, again a carry of 1, 1, 1. So you will be obtained with 1 and a carry 1. So 1 and a carry 1, you will get 0 with a carry 1. So here already just a carry 1. So here it is 1. Here 1, 1. So the product obtained will be 1, 0. No, 1, 1, 0, 1, 1, 0, 1, 0, 1. This is our product term, and which is plus 437. And this is the product which we also need to be obtained while multiplying 23 into plus 19. So this is how we are doing a both multiplication using the positive numbers. So in the previous slide I have shown how can we multiply two positive numbers using both algorithmic multiplication. So now just briefly I will be explaining you how this both algorithm is done internally in our computer. So first of all I would like to take a table which consists of some of these registers. So as we all know, registers are small space in our computer memory where our data is stored. So here I would like to take B as our multiplicand register and Q as our multiplier register. So you can see here our multiplier Q has a 5-bit operand, that is 1, 0, 0, 1, 1. This is a 5-bit operand. So as we all know that a register is taken as empty here, that is 0, 0, 0, 0 and 0. So this is our A register which is taken as empty. There is another register here which is shortly written as SC, which is sequence counter. The full form of SC is sequence counter, which will store how many bits are there in the counter. SC stores how many bits are there in the counter. So as we all know, we can see here there is 1, 0, 1. This is nothing but a 5-bit, because why this is it is in a binary form. When we convert this into a decimal form, we will be obtained with a 5-bit product, which is, you can see it is in a multiplier which is 5-bit, that is here 1, 0, 1. In a decimal form it is 5-bit, as it is there in a multiplier, that is 1, 0, 0, 1, 1. So moving on to our first, before that we need to also, I would like to tell there is another flag taken extra carry bit, that is E, and also SC, that is our sequence counter. It also maintains the track of how many bits are there in our multiplier. The main function or the main work which our sequence counter does is tracking how many bits are there in a multiplier Q. As I said you, there are 5 bits in a Q multiplier. So SE is 101, which is 5 in a decimal form. So let's move on to the first step. So as I said, our multiplier is a Q. So we need to see what is the rightmost in our multiplier Q. That is 1. So Qn will be 1. So when Qn is 1, we need to add our B. That is our multiplicand. That is 1011. So that is your first partial product. See, you can see in the cursor, this is your first partial product. After finding of this first partial product, then shift right E, A, Q. E, A and Q. You need to shift it to the right side. See, you can see here. See, 1 in first place it is 1, here it is second place. Here 0 is in a second place, but here it is in the third place. 1 is in the third place, here it is in fourth place. Here 1 is in fourth place and here 1 is in the fifth place. So shifting to the right side. So our multiplier becomes 11001, and this is a 4-bit, that is you have written in SE. We need not to do anything in SE. Just E, A and Q is shifted to the right. So it is 4 because we are now left with the 4 bit of the binary product, because 1 we have just consider it right now. So 1 determines, and then remaining will be 1001. So again we can see the 1 is the rightmost remaining term. So Qn is 1. So as I said in a previous step, when Qn is equal to 1, add B to the Qn. That is your second partial product. As you can see here, it is I have written, it is your second partial product. Now moving on to the third step, it is 0. So Qn is 0. When Qn is 0, we need not to add B to the Qn. We can just directly right shift E, A and Q. That is 0, 1, 0, 0, 0, and your multiplier becomes 1, 0, 1, 1, 0. So moving on to the fourth term, that is again 0. So Qn is 0. As I said, when Qn is 0, we need not to add the B, the multiplicand. You can just directly shift right E, A and Q. That you can see your multiplier becomes 0, 1, 0, 1, 1. And here it is 0, 0, 1, which is your counter becomes 1 bit. And then finally, Qn is remaining, the multiplier is remaining with 1. So your Qn will be 1. So when our Qn is 1, you need to add the multiplicand B, that is 1, 0, 1, 1. So when you add, you will get your fifth partial product, and this is your fifth partial product. So after finding out the partial product, as we know, shift right E, A and Q. So when we right shift E, A and Q, 0, 1, 1, 0, 1 is your A, and your multiply Q becomes 1, 0, 1, 0, 1, and your SC becomes 0, 0, 0, that is your 0 bit. Here it is 5 bit, this is your 4 bit, this is your 3 bit, this is your 2 bit, this is your 1 bit, and finally it becomes the 0 bit. And then our final product is AQ. AQ means A into Q. You need to add this both. So while adding, you'll be seeing that you'll get 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. See, and this is your final product. And this is the same product we've got it here in the last step, that is 437. So this is how the both algorithmic is done internally in our computer. So this is your final product. Here multiplicand B, and you have to take its multiplier Q, and this is all the procedures which is done internally in our computer. So and then moving on to the negative multiplier. So as I have explained you for the positive multiplier, in the same way the negative multiplier is also done. The only difference is the symbol, the sign changes in the negative multiplier. As we now have taken the example of plus 13 and your minus 6. So plus 13 is represented as 0, 1, 1, 0, 1. Minus 6 is represented as 0, minus 1, plus 1, minus 1 and 0. And as same as 0 multiplied, 0 is the minus 6 is the multiplier and plus 13 is the multiplicand. So for the rightmost term of the multiplier, which is 0, multiplied to the multiplicand, that is 0, 0, 0, 0, 0, and so on. The same way you need to multiply this both, and finally you will be obtained with the answer of minus 78. This is same as how we have done it in the positive numbers. So I think this is all about my topic today. And then finally the reference of my topic is from the Computer Organization by Carol Hammack and the Google as well as the YouTube. And thank you for listening to my presentation. Thank you everyone.